We've learned that we tend to want to confirm our beliefs rather than disconfirm them. This is the confirmation bias in action. Science deals with this in several ways, one of which is the system of peer reviewing of papers. The other way is the demand that scientific claims must be falsifiable. Scientists may be so enamoured of their theories that they only seek to confirm them. Each instance of a confirmation is pleasing, but ultimately there is no number of confirming instances that will show a theory to be correct. Scientists always formulate their theories in a way that is falsifiable. This means that there must be some way to express the theory, to say that under a particular set of achievable circumstances, if a particular outcome occurs, then the theory is wrong. It is that set of circumstances that is the first port of call for experimental design. Scientists prefer to test in circumstances where the theory will fail rather than succeed. The philosopher of science Karl Popper promoted falsifiability because it is an instance of deduction in science rather than induction. Here's a good example from the history of science that demonstrates the value of falsification, slightly simplified. It was thought in the 19th century that all of space was filled with a mysterious substance called the ether. Scientists thought this because light seems to have wave-like properties, and it was thought that waves had to be a vibration of something. The something that was vibrating when light moved through space was the ether. Since sound was the vibration of air, for example, by inductive analogy, light was the vibration of the ether. Two scientists, Michelson and Morley, came up with a clever experimental design. They wanted to use two lasers that sent out beams of light at right angles to each other. Their reasoning was that since the Earth is moving through the ether, one of those light beams would be against the direction of the ether stream, and the other would be at right angles to it. The one against the stream, in the direction of the Earth's movement, would be slower. If this was not the case, then the concept of the ether could be discounted. Turns out the light beams travelled at the same speed, and the concept of the ether was shown to be false. The theory was falsified by experiment. Rather than seeking confirming instances of how light moved through space, the part of the theory sensitive to falsification was pointed out, and it was that weak spot that was tested. In general, the deductive nature of the experiment looked like this. Premise 1, a light wave is a vibration of a medium called ether. Premise 2, waves moving along the direction of movement through a medium must seem to travel slower than waves moving at right angles to it. Conclusion, light moving along the direction of movement through the ether must travel slower than light moving at right angles to it. The argument is phrased as a valid argument. If the premises are true, the conclusion must also be true. But is it sound? Experimentally, the conclusion was found to be false. Therefore, at least one of the two premises must be false. Premise 2 was already well known, so the weak spot was premise 1. Light does have wave-like properties, so it must be the assumption that the ether exists that is incorrect. Using falsification, we can have deductive certainty from an experimental observation. This is in contrast to inductive reasoning, which cannot provide such certainty. It's widely held that any scientific theory must be falsifiable. It is a defining characteristic of how science works that theories considered unfalsifiable are not really scientific theories. We'll see shortly how this is an important discriminator when talking about pseudoscience.